Okay, so the last class we talked about all the techniques about how to purify the protein size, ion, surface charge, affinity chromatography, also salting out. So I mentioned before that case study, how these protocols are used. Before going into actual case study, I have to explain a brief thing about this one. So because the reason I explained this one in advance before going into the case study is the following. Because you have now, for example, the E. coli. This is a bacteria that producing the protein. For example, you can imagine insulin or growth factors that for the therapeutic drugs as a protein drugs. Erythropoietins and TNF alpha that I mentioned in the coronavirus classes also. E. coli produce it. So E. coli has a plasmid and protein make out of this from the plasmid. Also, the E. coli has this is a dividing actually active living things, and then actually chromosomes are their host chromosomes, and this is plasmid. And a lot of proteins and things are existed, right? So the reason for this and how we separate DNA versus proteins. This is things. So remember the question to answer these questions. Remember that's why we discussed in before about the size of the biomicromolecules in previously, because that reason is DNA generally speaking is very very long and very very large. Even if their total diameter, I should say, if the DNA is a very very thin diameter cylindrical structure, then diameter is very small, but the overall size is very very long and big compared to the protein. So how we do it then? This very smart technique biochemists chemists develop. They use simply pH. They use the pH. So the pH is simply the DNA. If you have DNA as phosphodiester, every single unit of the ATGC has the phosphate charge, which is anion polymer. Then, generally speaking, this is pH 7 because it's all the life is living in a neutral condition. 7.4, about 6.5, 6.8. But anyway, nearby the neutral pH condition. Then if pH is increased, say pH 7.0, then we increase pH pH about 11, 12, even 13 by adding sodium hydroxide. So what will happen is, in the DNA here, you have all the A, T, G, C, all the mean containing things. Even this phosphate has a OH here, even negative. So all these are molecules, the groups, proton containing groups are deprotonated. That means no protons in here because the pH is extremely high. See, the OH, you high or minus, SH become S minus, NH3 plus become NH2. What else? Something like this. All the deprotonations is going on. So this is phosphate, hydroxyl, whatever the hydroxyl from the serine, from the amino acid, anything O minus. So it becomes, if you have this extreme alkaline pH, this DNA would be extremely strong anion. Extremely strong anion. But when you decrease the pH back, so now I'll delete this one. And then this pH goes back to pH 6 or 7, back to the original pH. But the thing is kinetically fast. Kinetically fast. So that means when you increase the pH from the 7, so I'll take a little bit, I'll just make things clear. Okay, there's 3 things. When you have this neutral to alkaline, you slowly add base, which is sodium hydroxide. So all the system are thermodynamically equilibrium. So slow and step-by-step deprotonation is going on. And then when you add the acid, for example, this one is acid, so now HCl is added here. Then it's relatively fast. You add very fast, large amount of sodium. The HCl is added to this solution. So then it suddenly goes back to the protonated state. But it's not a slow state. You can protonate all the residue ATGC and phosphate OH and everything's here. Step by step OH recovering back to the original state. It's not that case. You add so much amount of HCl, then everything goes back. Then some are protonated, some are not protonated. So that means there's all messed up conditions in here. That is what things happening is such a large molecule has a hydrophobic interaction. So they extremely strong anionic state of DNA. They well extended structure because of the so strong and negatively charged repulsion forces going on. But suddenly you go back to the pH, so protonation is going on. Then that area which is protonated becomes non-charged state, and then you start to aggregate. If you do this step, kinetically fast step, it is slowly, which is a thermodynamically equilibrium state, back to back slowly. Then this aggregated DNA or RNA is not found actually. So this speed is very important. So in the system that you have now, you have a DNA plus protein. Protein is a relatively small molecule, doesn't happen of the system. But denaturation and renaturation is going on probably, but this is a single protein level. But DNA is so much, maybe 100,000 times is a longer in size. So this aggregated DNA is found when you go back to the pH is a normal neutral system. Okay, so that would be included protocol, because you have a cell that E. coli producing the protein. You're going to break down the cell, then they release it to solution. You have a DNA, proteins, everything, lipid, cholesterol, and things, vitamin, then there's a mixtures. Then how you purify the DNA is this one. This one is very simple. Simply increase the pH and decrease the pH. Yet very effective method to purify the separating DNA and protein. Okay, let's begin with the actual protocol, how to purify the PYP in this case. The number 1 is the harvest cell through the centrifugation at 5,000 to 6,000 RPM in the solver for 10 minutes. So this one is now you have E. coli in the solution, and then you put this tubing into the centrifugation machine, and then you rotate this centrifugation machine with the round per minute rotation RPM 5,000 or 6,000. So during which this gravity force is now applying to the solution. The E. coli is heavier than water because its density is greater than 1. So they actually E. coli end up with at the bottom of the tubing. So and then you end up with actually the solution remaining on top, which is called the supernatant, which is after centrifugation decant supernatant. So decant means to throw that away, because at the bottom you have all the collecting the E. coli. So they measure the weight to calculate the weight of the whole cell. So you can actually measure the overall weight of the E. coli you can collect by this step. Okay, so number 2 is the resuspending the cell pellet. It means you bring the pipette, and then because the E. coli is at the bottom, and then you pour the additional solution, not new solution, which is 50 millimolar sodium phosphate, pH 7.2. This is new solution. You can define the pH and control the pH. And then you bring the pipette, and then you stir the pellet E. coli resuspending back to the solutions, because you imagine you can like some sugar powders in the bottom. You can stir this, then going back to the solutions again. And then after resuspension, this is called a resuspension. Collect the solutions in one beaker. Number 3 is sonicate the cells by immersing the tip for 1.5 minutes. So this sonication means this is the kind of step that breaking the cell membrane. The sonication means you're providing the sound, but the sound is high frequency, so that you can mechanical forces exert applying to the cell membrane. So you can imagine like situations you go to the bar or go to the club, then you go in approaching the speakers, and you actually feel the mechanical force out of the speaker now. Similarly, they use sonication providing the mechanical force to the cell, so cell membrane actually lipid bilayer break. So the lipid bilayer break, then basically this step providing the heat in the solution. That's why, and then in the protocol mentions, and then rest 1.5 minutes in an ice, because ice be quite cool down the solutions. Then remember, this ultimate goal is protein purification. Protein basically denature as the temperature goes up. So you don't want to have the situations. You have to maintain the solution temperature as low as possible. Even as best is actually 4 degrees, but is lower than ambient condition. Ambient temperature is always recommended. And then repeat this sonication process 3-4 times until the color solution turns into the dark brown. So originally the solution looked like it's slightly yellowish, but when you cell membrane break, this overall color of the solution becomes a dark brown. Next, number 4 step is this is the step that actually 4, 5, 6 step is the one that I previously mentioned in the whiteboard at the beginning of this class. So let's do again. Increase the pH. Remember that until the step number 3, then you resuspended the E. coli solution, and then you sonicate it to break the cell membrane. So internal, all the DNA, proteins, liposome, actins, plasmid DNA, vitamins, and those things are in the solution. So there's no cells anymore. So now they increase the pH to about 11 with a 10 molar sodium hydroxide, and then incubate for 5 minutes. So this is the slow step increasing pH from the 7, because we add in second step sodium phosphate buffer pH 7.2. So now the pH is 11. And then also the important thing is, remember the volume of 10 molar sodium hydroxide, because when you're gonna actually put back to the pH, original pH is back, then as I mentioned before, you're gonna now separating DNA and others. Then DNA precipitating out, and then the viscosity change it. So the viscosity change it, so that you see overall solution, this viscosity is increased, so this situations actually is difficult to measure the exact pH value for this situation. So it has to be, remember the overall volume of the sodium hydroxide you added in the step 4. Okay, so the step 5, the readjust pH with 10 molar HCl. So 10 molar sodium hydroxide in step 4 and 10 molar HCl in step 5. And it is a step that pH go back to the original pH 7. Okay. And then now you'll see the overall viscous solution. You'll see the DNA is precipitating out all the messed up things you can observe. So now it's time to centrifuge again. So now the step is spin. Spin means a centrifugation. The lysate for the 15 minute at 15,000 RPM. This is a step actually you're precipitating DNA. So you want to separate the DNA from the protein solution and then continue with the supernatant. Supernatant means it's an up solution, not a precipitated pellet. So your protein is inside on the top of the solution, which is a supernatant. So you're gonna working with the supernatant solutions, not a precipitate. Sometimes you work with a precipitate, the pellet system, but in this case is a supernatant. You want to use it. And then check the pH again. If the pH is not located between 6.5, 7.5, then you fine tune the overall pH about 7.0.